Distribution is another one of those key fundamental concepts that the GMAT likes to test often. It's related to both factoring and multiplication. So we're going to look at how it can help us do multiplication a little more easily, and then how we can apply it to difficult addition problems. So looking at this first equation here, we have 735 times 5, which means we have this could also be represented as 5 times 700 plus 30 plus 5, because the interior here would be 735. And we solve parentheses first when we're doing PEMDAS, which is the order of operations. So 5 times 700 plus 5 times 30 plus 5 times 5 is another way of representing this. And that's the idea of distribution. You essentially hand the 5 off to each of the components and keep them added together. So we would get 5 times 700 is 35 with 2 zeros after it. 5 times 30 is 15 with 1 0 after it. And 5 times 5 is just 25. Add these all together and you get 3,500 plus 150 plus 25 equals 3675. So that's how we can use distribution to make difficult multiplication a little bit easier. All right, now looking at this second situation, the GMAT likes to test distribution with exponents because it's an awkward situation. We don't have a good rule for exponents when we're dealing with addition between them. And so what we end up doing is we end up pulling out the greatest thing that they have in common. And that's the same thing we did here with the 5. So if you were given this situation initially with the addition in between it, you could pull out the 5s from each of them and turn it into a formula that looks like this, with just one 5 sitting outside and then a bunch of components on the interior. And then finally represent it like this by adding up those interior elements. So we're going to do the exact opposite here, or the exact same as what we just discussed, but the opposite of what we did in the first equation. So I'm going to pull out the greatest common factor of these two numbers, which is the least of the exponents, and that's 5 to the third. So 5 to the fifth is the same as 5 squared times 5 to the third. And 1 times 5 to the third will give me this 5 to the third here. And so this is the same as this expression just simplified. And now I could also represent this as 5 cubed times 25 plus 1, which is 26. And so the GMAT might ask you, what is the greatest prime factor of 5 to the fifth plus 5 to the third? And the answer looks like it would be 5, but it actually ends up being 13, because 26 is 13 times 2. And the reason it's not 5 is because we have this addition situation taking place, which means that we might get some unique sort of factors that we weren't expecting. Now, it gets even trickier when we have negative exponents, because you'd expect to pull out the 5 to the negative third. But always remember to pull out the least of your exponents if you're dealing with exponent questions. So you would pull out 5 to the negative 5. And if we look at that, that would be times 1 to get this situation. And then times 5 to the positive 2 to get this 5 to the negative 3. Because when you multiply common bases, you add the exponents together. And so 5 to the negative 5 plus 5 squared equals 5 to the negative 3. And the reason we pulled out the least exponent is because that allows us to add together whole numbers in the interior. So we're going to get 5 to the negative 5 times 26 again, and that is another way of representing this situation. So it depends on what the answer choices look like. That will determine how you want to solve the equation. But just from my experience, the best way to attack it is to pull out the least exponent if you're using distribution with exponents with common bases. And the tip to use distribution is if you see addition or subtraction in the middle of two numbers that have common factors in play.